My name is Barati. It's my pleasure also on behalf of the co-authors to shortly present to you the results of our study titled as Living Light Interfaces, an Exploration of Bioluminescence Aesthetics. Our paper introduces the concept of living light interfaces as a new research space focusing on new aesthetics and interaction qualities of bioluminescent microorganisms. As an initial attempt in our exploration of living light interfaces, we focused on a specific strain of dinoflagellates called Pyrocystis fusiformis. The work builds upon the existing frameworks and notions within the emerging fields of bioHCI and biodesign, namely living bits and living material interfaces, and takes interest in the temporal dimensions of material aesthetics in connection to the previously introduced concept of ephemeral user interfaces and our recent work on living artifacts, where living aesthetics become an important design focus. It also reviews the state of the art in dynamic light characterization to identify the relevant qualities when characterizing algal bioluminescence. There is a great deal of publication on the science of bioluminescence, particularly in the field of marine biology, and already a number of designers and artists have incorporated these organisms in their installations. Bioluminescence in dinoflagellates is known to occur when shear stress is induced on the cell, for instance when larger animals swim by or waves break on the surface. Please check the paper for more information on any of the related topics. For sake of keeping within the time, I will move directly to our experiments. For our experiments, we worked with Pyrocystis fusiformis algae cultures from pyro farms, which we kept in sterile Erlenmeyer flask capped with non-absorbent cotton balls. In the middle image, you can see the visible changes in the culture over the period of 8 weeks as the algae cells grow in number and metabolize. In order to effectively grow and maintain the dinoflagellate cultures, we kept them in a modified wine cooler, which allowed for a constant temperature between 14 to 16 degrees Celsius and a controlled lighting regime. A lighting regime is crucial as photosynthetic dinoflagellates are regulated by a circadian clock. Besides the controlled temperature and light conditions and the sterile and breathable containers, the culture needs nutrients every 4 to 8 weeks to stay alive. We have designed an orbital shaker to perform different but consistent types of kinetic stimuli. Here you see a video of a shaker in action. To induce vibration, a wooden plate consisting of 7 small piezo discs was prototyped that could be mounted on the same base and controlled with the same operating panel. Eighteen variations pattern within the 3 main types of stimuli, namely rotation, pulse, and vibration, were tested in this study, as listed in this table. In the remainder of the presentation, I will present some of the results and show the video footages to supplement the results presented in the paper. For intensity variation over time, the video footages were analyzed frame by frame using an existing MATLAB script, which calculates the mean luminance value of all pixels within each frame and plotted the values over time. The presented graph compares the intensity variation of the 90 and 120 RPM rotational speeds. As evident in the corresponding video, the peak value in 120 RPM is up to 4 times greater than the peak value in 90 RPM, while the total light output is almost double. Adding intervals to the 120 RPM rotational stimuli resulted in an interesting observation. As shown in the graph, the total lightness increased around 15% in case of paused rotation. The direction of rotation has also an impact on the intensity variation. As clearly depicted in the graph, in the first 5,000 milliseconds of video footages, overall the mean luminance value of alternating rotation is 2 times greater than paused rotation. Our experiments show that the duration of light emission is influenced by the type of stimuli, while the longest was attributed to rotation and the shortest on vibration. Overlaying the response curves as output, in relation to the mechanical stimulation as input, we noticed that the initial delay in response was affected by both the type of mechanical stimuli and the prior condition of the liquid culture. A culture which had not been stimulated before compared to a previously stimulated one resulted in shorter delay in response. Particularly, once a culture is exposed to a large shear force, such as a high-speed rotational movement, as shown in the video, it shows almost no bioluminescent response to following more gentle stimuli. But think that this behavior could be explained by organisms' loss of sensitivity. We use long exposure trajectories of the moving light pattern and frame-by-frame propagation of the pattern to report the difference across kinetic stimuli, namely rotation and pulsation. Previously, researchers used fluid dynamics models to describe the dynamics of the observed light pattern. Our results attest to such a mechanical relationship between the fluid dynamics and the emergence and propagation of the living light pattern. Thus, any parameter that governs the fluid dynamics, including the shape of container and volume, can have influence on the spatial propagation of the living light. The last cluster in our flash characterization study is textural qualities, which concerns the perceived texture. According to our close-up images of the local areas, type of stimuli, speed, and condition of culture has an influence on the textural qualities. As the rotational force pushes most bioluminescent cells into a tight cluster near the edge of the glass, the resulting light texture is a uniform glow with barely any visible individual dots. Pulsation and vibration tend to create highly textured lighting patterns, as cells throughout the whole liquid are triggered but not pushed together as much. Expectedly, speed of rotation also had an impact on the visibility of the algal individual flashes. Another interesting biological factor was the age of culture. Over time, the culture is clustered by the metabolic processes of the cell, which clearly had an impact on the textural quality as shown in the video. So on the right, you see the fresh culture, and on the left, an aged one. To conclude, our paper presents a study of the living aesthetics of bioluminescent algae in a liquid media. To that aim, we used 18 variations of rotation, pulse and vibration kinetic stimuli. Further research could focus on studying people's interacting with living light interfaces in real-life settings, while our exploration involved simple kinetic stimuli. More complex range of stimuli with the support of modeling and simulation tools can be a next step to support designers' better understanding of the textural qualities and spatial distribution of a living light. In the attempt to make our characterization result accessible to a wider public, we designed a living light interface for the exhibition Still Alive. In the video, you see the first iteration of the design, which incorporates a metal frame and stronger DC motor. For the next iteration, we plan to map the kinetic stimuli to input from visitors by incorporating ambient sensors. With that, we hope to further explore the links between living light qualities and the fundamental concepts of interaction, such as input and output. Thanks for listening.